Hello everyone, welcome to our group. Today, our group consisting of myself, Najmi, Suresha, Aida and Shamimi are excited to introduce our project, Disease Spread Simulator, a probability-based approach to disease transmission. Under the topic of probability, we designed a model to simulate how an infectious disease moves through a population over time using mathematical principles.
Now let's look at the basic concept of probability. Probability helps us determine the chance of an event occurring. In our project, probability helps us calculate the chance of a disease spreading. The formula for probability is probability equals the number of favorable outcomes divided by the total number of possible outcomes. For example, if 3 out of 10 people become infected, the probability of infection is 3 divided by 10, which equals to 0.3 or 30%. This means that there is a 30% chance of a person becoming infected in this scenario. Using probability allows us to analyze possible outcomes and better understand how disease may spread within a population. Next, let's move on to conditional probability. Conditional probability is the probability of an event happening when another event has already occurred. For example, what is the probability of getting infected after having contact with an infected person? The formula is P of A given B equals P of A intersection B divided by P of B, where A represents a person becoming infected, B represents a person having contact with an infected person. Based on the example shown, the probability is approximately 14%. This means there is about a 14% chance of becoming infected after contact with an infected person.
As you can see, independent events mean one doesn't affect the other, like tossing a coin and rolling dice. But disease transmission is usually dependent. Exposure to infected people increases risk, while vaccination reduces the probability of infection. Next, the SIR model divides people into 3 groups: susceptible, infected, and recovered. Susceptible are those who can be infected. Infected are currently sick, and recovered are immune or removed. 2 key parameters are beta, the infection rate per contact, and gamma, the recovery rate per day. The ratio beta over gamma determines how large an outbreak can become.
Now will I explain how our MATLAB simulator actually works. Our simulator takes 3 inputs: the population size, the infection probability, and recovery probability. These values control how simulation behaves once the inputs are set. The simulator follows 5 steps. First, it starts with the infected person. Then each day, it calculates the new infection based on the infection probability. Next, it's calculate the recoveries using the recovery probability. After that, it's update using 3 ASR, which is SIR groups that susceptible, infected, and recovered. Finally, it displays the results using the graphs. We can see how the disease spread over the time. Process repeats daily until the simulation ends. This slide shows the actual MATLAB code we used for our simulation. The code starts by initialing all the parameters: the total population, the number of the initial infected people, the infection rate, the recovery period, the number of days simulated. And then create arrays to store the daily values: susceptible, infected, and recovered individual. It's using a loop. Code runs day by day, calculating the new infection and recoveries, and then updating the population values accordingly. Finally, it generates a graph that plots all 3 groups over the time, so we can clearly visualize how the disease spread eventually slows down.
Moving on to the next slide, we can see here the output of our MATLAB simulation. This graph tracks a population of 1,000 people over a span of 50 days. The blue line represents our susceptible population, which starts at maximum but then rapidly drops as the disease takes hold. The red line represents the infected population. As you can see, because of our transmission probability settings, infections rise sharply and peak around day 12 with roughly 740 people infected simultaneously. Finally, the green line represents the recovered individuals steadily increasing over the 50 days as people fight off the virus. This visualization perfectly captures how a high probability transmission rate can quickly overwhelm a population if left unchecked. To conclude our presentation, we learned that probability is highly effective at predicting disease spread. And specifically, conditional probability helps us explain the exact risk of an individual becoming infected after exposure. Furthermore, we have proven that MATLAB can successfully simulate these complex real-world scenarios, proving that lowering the base infection probability is our best tool to control active outbreaks. Looking ahead, we want to expand this simulation with 3 key future improvements. Firstly, we plan to factor in a vaccination rate to see how immunity alters the curve. Secondly, we want to simulate multiple disease variants interacting at the same time. And lastly, we want to build a dedicated graphical user interface, or known as GUI, to make the tool interactive for everyday users. Thank you so much for listening. That's all from us. Thank you.